Okay, so this is the first video of me going through the Jones final exam practice test, and this is question 1. So question 1 is about crystal symmetry, and part A asks you to sketch the point lattice given the image. So I personally like to pick, the first step you want to do is pick one point on one of the bricks or one of the tiles or whatever you're given, and consistently pick that same point. So in my case, I'm doing the center of them. So I kept picking the center of each brick until I got a repeating pattern. So now I have this square with a point in the middle of it. This is the C pattern. So this is not what the question is asking, but it's going to eventually get to that point. But so part A, we have sketching the point lattice, and that's just going to be, let's make sure we have the distances right too. The distance between these 2 points and these 2 points may not be the same. So let's go ahead and make sure that is made clear. All right, so one other thing that I want to point out is if you go ahead and draw this as a square, like a point here, point here, point here, point here, point here, you're going to insinuate that there is fourfold symmetry when there actually isn't. So you don't want to draw it like this just in case, because if you rotate this by 90 degrees, it would look exactly the same. But if you rotate this by 90 degrees, it wouldn't look the same. So just go ahead and make sure that this distance right here and this distance is a little bit different so that you can tell that when you've rotated at 90 degrees, there's something different about the structure. Okay, so that's part A. Part B says sketch the basis composition and the position relative to the lattice. Okay, so the basis is a singular brick, rectangular, and I'm going to say this is 0, 0, and put it at 0, 0. And just in case, I'm going to say I'm going to say this is a 0, 0 point, and this is going to be at 0, 0. All right, that's that. Part C says, what symmetry elements are present? Example, rotational symmetry and mirror planes. Okay, so this is all building up to all of the C2mm, P2mm, C6, whatever. And the symmetry that's present is C, which is what I talked about in the beginning. Why? Because you have a square, right, or a rectangular shape with a center in the middle, or whatever shape, actually. You could have a C6. You could have a hexagon with a point in the center, and that would also be a C because of that center point. So C for center, it's easy to remember. So C, how many rotation, this is C symmetry. And then rotational, it's going to be how many fold? Okay, well, let's see. If I take, we'll go ahead and draw this so it's easier to visually see. It's going to be, if I go ahead and take this pattern, which is essentially this applied to a basis, and I rotate it 90 degrees, you can easily tell that something has changed. So it's not fourfold, but if I rotate it 180 degrees, that looks fine. So that means that this is a twofold rotational symmetry. Cool. Now part D says, what point group does this belong to? Oh, sorry, I also missed the mirror planes. So the mirror planes, if we had a mirror here, everything across would be the same. So there's one right there. Another one is this right here. Everything across this reflected is the same. So we have 2 mirror planes. Notice how this is not a mirror plane. Why? Because if you were to reflect this across, let's go ahead and actually draw it again. let's say you were going to say, all right, well, this is also a mirror plane. Well, if I took this point and I brought it over here, that wouldn't be the same. If I took this slice and I reflected it, it would look something like this. Which is definitely not the same thing. So just make sure you're not thinking that there are mirror planes when there actually isn't any. So we have two mirror planes. This right here is not actually necessary to say, but it's going to lead into the next part. All right, and our 2-point symmetry group is going to be C because of what we described before, 2 because of the fold of symmetry, the rotational symmetry, and then an M and an M for the two mirror planes. And that's it. All right, question 2 tests the structure factor stuff we talked about I think a week or two ago. So question 2 says, cobalt oxide nanoparticles finding everything in microbatteries. Whatever. XRD. Okay. You evaporate the solution and place the residue in a glass for XRD using copper K alpha. That's going to be used for later. So lambda is equal to 1.54 angstroms with an A naught of 4.26 angstroms. Based on the picture below, what are the positions of the lattice points in the unit cell? Okay, so let's go ahead. I'm going to go ahead and color code our atoms so that we can go ahead and see what actually is going on. Okay, so just looking at this, it may be a little bit hard to see. So I'm going to go ahead and, actually, I'm going to go ahead and color code the other color. Let's color code the corner first. I feel like that's what we're most familiar with. So you can see, if you're starting to notice, we have one on each corner, right? We have an atom on each corner and one on each face, making this an FCC. So an FCC N is equal to 4. The number of atoms that fit in an FCC is 4. So the number of lattice points, full lattice points, in an FCC is also 4. So in order to answer this question correctly, you should have 4 points. No more, no less. So we picked the cobalt, so let's go with the cobalt. So for a cobalt, actually let's go ahead and just write, we have a 0, 0, 0, 0, actually, I'm going too fast. So now we're going to take the same method I talked about before, and that's that eighth of a cube method. So you go ahead and take that corner right there. It may be a little bit hard to see, so I'm going to go ahead and redraw it. That's going to be so you're going to have a cobalt here, 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 and here. And every other position you're going to have an oxygen. All right, so from this, you can see where the cobalts are, because that's what we care about. You could have picked the oxygens and given the lattice point of the oxygens, and that's totally fine. Just make sure you give one or the other, not both. So, personally, I like to go with the one at 0, 0, 0 because that never fails you, and you don't want to deviate from what you normally do during an exam. So, the points here are 0, 0, 0, 1 half, 1 half, 0, 0, 1 half, 1 half, and 1 half, 0, 1 half. And how I know that is I'm assuming this is X, this is Y, this is Z, and this entire length and width is essentially one entire lattice constant. So I'm saying 1 half because we took an eighth of that cube. All right, so now we have our eighth, and from this we found the points. and that's going to be a 0, 0, 0, 1 half, 1 half, 0, 0, 1 half, 1 half, and 1 half, 0, 1 half. Right, so part B says, what is the basis, composition, and position? This is where you start, this is where you essentially pick the points that you want to describe as, hey, this is the basis. This is what I'm applying to this lattice. So the basis is a cobalt and an oxygen, right? You're taking an FCC and you're adding a cobalt and an oxygen to it. So your basis is going to be cobalt, oxygen, and how you can always figure this out correctly is just look at what's in the unit. If there's 2 atoms in the unit, there's 2 bases. If it's O3, for example, there's 1 barium, 1 titanate, and 1, 2, 3 oxygens. So you have 5 atoms in the basis. This is the safest way to go about it, so just go ahead and do this if you want to make it easier for yourself. Right, so now we have a cobalt at 0, 0, 0, and oxygen at 1 half, 0, 0. That is this point right here. So that's the basis and the composition relative to the lattice points. All right. What is the crystal? And you don't have to actually list out all of these because you've listed them in the last step, and it's saying relative to the lattice points. So it's already saying, okay, I'm going to put a cobalt in the 0, 0, 0, and 1 half unit over, I'm going to put an oxygen. Now this is going to apply in every single place in that lattice, because anytime you look at a cobalt, 1 half over and to your right is always going to be an oxygen. Even here, 1 half over, there's an oxygen here that we didn't draw. So just do the 1 point. Okay, what is the crystal structure of the cobalt oxide, and what is the total number of atoms? All right, so the crystal structure is FCC, and it's an interpenetrating FCC. If you can also say that is a zinc blend. It's not a. I'm sorry, it's rock salt. I think it's the same as NaCl. I think it is rock salt. So, yeah, so it's, regardless, you can just say FCC and that's the right answer. And what are the total number of atoms in the unit cell? Okay, well, we counted it here. The nice thing about doing the eighth of a cube is that you can actually figure it out. You have 1, 2, 3, 4, 5, 6, 7, 8, sorry. Cobalt. Sorry, yeah, it is. It is going to be 8. Yeah, okay. Just wanted to double check. And that you get from just counting the number of atoms. All right, what is the structure factor equation for cobalt oxide, and what are the first 2 planes that diffract? Okay, so we know it's FCC, so we have essentially an idea of what's going to diffract, and that's going to be the 111, the 200, and all of the other ones that are either all even or all odd. So let's just go ahead and make sure we have our structure factor calculation right. So F is equal to F cobalt e to the 2 pi I. I'm going to go ahead and pull out all the F cobalt. Actually, I'll just rewrite everything. E to the 2 pi I HU plus KV plus LW plus F oxygen e to the 2 pi I HU plus KV plus LW. All right. So from here, I'm going to go ahead and right here, actually, sorry, I'm going to go ahead and write where all of these atoms are and their position. So, because it's asking for the atoms and their respective positions. So, where is cobalt? Cobalt is going to be at all of these that we talked about here. So, it's going to be at 0, 0, 0. Gotta write it out again. oxygen is going to be at everywhere that's 1/2 over. So we can just add a 1/2 0 0 to all of these points. So let's go ahead and do that. That's going to be a 1/2 0 0 here. A 1/2 0 0 plus this value right here is going to give us a 1/1/2 0. When we're doing things like this, if we ever get a 1, we can just turn it back into a 0. This is because, if you think about it, a 1 0 0 or 1/1/2 0, whatever, is going to be somewhere in the next unit cell. And we don't care about the next unit cell. We can just say, hey, we're going to come back to where we were, which is right here. All right. Or in this case, this is the point that this is talking about. All right, so we're going to add 1/2 0 0 to this point now. And that's going to be a 1 or 0 0 1/2. And the next one, finally, is going to be adding another 1/2. It's going to be 1/2 1/2 1/2. Great. You could also figure out these points by literally looking at the eighth of a cube that we drew and actually writing the coordinates of these orange dots. But whichever one works better for you. Cool, so now we have our points and we can find our structure factor. FCO. I'm going to pull all of those out because we're going to have multiple of these. Since we have 8 atoms in our unit cell, we actually also have 8 terms in the structure factor equation. So I'm just going to pull this out. We're going to get 4 terms from cobalt, 4 terms from oxygen to add up to 8 total points. So e to the 2 pi I h, so let's do the first point right here. H times 0 plus k times 0 plus L times 0. Cool. E to the 2 pi I. Next point. 1/2 1/2 0. H over 2 plus k over 2 plus L times 0. These are, by the way, these are our U, our V's, and our W's. So that's why I'm multiplying them, as I said I would do here. Right, next one. E to the 2 pi I h times 0 plus, it's going to be this one right here, so it's not going to be 0, sorry. H times 1/2 plus k times 0 plus L times 1/2. And finally, our last one is going to be e to the 2 pi I h times 1/2. I'm sorry, 0, h times 0 plus k times 1/2 plus L times 1/2. And this is just our cobalt. So this seems like a lot, but if you simplify it, you can just get e to the 2 pi I raised to the 0 is just 1 plus e to the 2 pi I h over 2 k over 2 plus 0. These 2's can be canceled out with that 2 outside, so we can just say e to the pi I, because that 2 got canceled, h plus k. And the same for the other ones. Next one's going to be h plus L, k plus L. So that's for cobalt. We're going to go ahead and do the same thing for oxygen. I'm going to go skip this big step right here and just go ahead and write it. It's going to be e to the pi I h plus e to the pi I k plus e to the pi I L plus e to the pi I h plus k plus L. All right, so there's the oxygen structure factor calculation. You can go ahead and pause and redo it and make sure you get what I get, but I'm just going to keep going. So I'm going to clean up everything a little bit. We're running out of space. Take away all the extra bits. And we end up getting this plus this as our structure factor equation. So the first planes to diffract we know, because it's FCC, is 1, 1, 1 and 2, 0, 0. Why? Because we had our list of planes that we always check. The 1, 0, 0, the 1, 1, 0, 1, 1, 1, 2, 0, 0, and so on. The rule for FCC is that if everything is odd or everything is even, it's going to diffract. The first two for which that rule applies is the 1, 1, 1 and the 2, 0, 0. So that's why those are the two planes that diffract. So you intentionally go ahead and pick those two planes to make your life easier. So we say F111 is 1 plus e to the pi I times, all right, so now we have an h and a k. Our h here is 1, and our k is 1, and our l is also 1. So it's just going to be 1 plus 1, which is 2. Plus e to the pi I, h plus l, which is 1 plus 1, 2. Plus e to the pi I, oh, sorry, there shouldn't be a 2 there. And then once again, 2. Same thing for oxygen. We have e to the pi I times 1 plus e to the pi I times another 1 plus another e to the pi I plus e to the pi I times 1 plus 1 plus 1, or 3. I'm going to go ahead and simplify this by saying any multiple that is an odd is going to yield e to the pi I as negative 1. If it's even, it's going to be positive 1. So it's going to be f. I'm going to go ahead and just replace them here. So this, it's a even number, so we're going to just replace it with 1. Same thing for these two. So they're all 1s. Which means this is equal to 4. Now we have some more space. Alright. Now all of these multiples are odd, which means all of these terms are negative 1, which means the inside is going to be negative 4. Meaning, for 111, the structure factor calculation is cobalt times 4CO minus 4F oxygen. Right, F200. You do the same steps and you end up getting 4CO plus 4F oxygen. Just go ahead and double check that. Yep. Awesome. So we were able to determine the, what other thing I would like to point out is that these all both do not equal 0, meaning that they diffract. This again confirms that the 111 and 200 diffract. Okay, so part E. Part E, you're going to need a couple equations. You're going to need D is equal to A naught over the square root of H squared plus K squared plus L squared. You're going to need lambda is equal to 2D sine theta, which is Bragg's law. And you're going to need the Lorentz factor equations. And that's going to be 1 plus cosine squared 2 theta over sine squared theta, cosine theta. Awesome. So let's go ahead and start. So our HKLs are the planes that we found in the last problem that diffract. And that's going to be 1, 1, 1, 2, 0, 0. All right. Our D's are going to be the A naught that we were given in the very beginning, this right here, 4.26, divided by the squares of the indices from our HKL. So this is going to be the square root of 3 for 111. And for the 200 is going to be 4.26 over 2. Right. So that gives us, go ahead and calculate these, 4.26 divided by the square root of 3. That's going to be very small, 2.46 angstroms. And for 200, it's just going to be 2.13 angstroms. All right, our theta we find using Bragg's law, which is going to be the inverse sine of lambda over 2d. All right, so our lambda was 1.54 angstroms, which we got from above, so 1.54 over 2 times the distance we just calculated, so these two distances. So let's go ahead and calculate those. We get for the 111, we get 1.54 divided by 2.46 is equal to, and then we're going to take the inverse sine of that. Gives us 18.24 degrees. All right, other one, we're going to say 2.13 equal to, and then 1.54 divided by 4.26, and then the inverse sine of that is going to be 21.2 degrees. All right. So sine theta over lambda is necessary for the table from which we're going to find these two values. So that's why we're calculating it. Every column relates to the column before it. So sine theta over lambda is going to be just rearranging this Bragg's law equation into sine theta over lambda is just going to be 1 over 2d. All I did was rearrange this. So we're going to double the distance and take the inverse, and that's going to be how we figure out that value. So let's go ahead and do that. All right, 2.46 times 2. I'm sorry. Yes, 2.46 times 2, and then 1 divided by that. 0.203. And then we have 2.13 times 2. 1 divided by that. 0.235. All right. So now, using these two values we just found, we're going to go to the table corresponding, the table that we're going to find little f from. So we can use the ions if we know the compound is an ionic, or you could use the regular element if you're unsure. Either way, Dr. Jung said he's not going to take off points. So in this case, because I know cobalt oxide is an ion, I'm just going to use the corresponding ion little f values. So in this case, we're actually going to have to interpolate, and I'm going to go ahead and highlight the values we need. So the reason why we need to go in between 2 and 3 is because for the 111, our sine theta over lambda was 0.203, which is between 0.2 and 0.3. And for the 200, it was 0.235, which is once again between 0.2 and 0.3. So we're going to look at 0.2 and 0.3 corresponding values to try and interpolate the answer. So we have 5.5, 3.8. Go ahead and write these down. I'm going to write it here. So I'm going to say FCR at 0.2, 0.3, and then cobalt 2 plus, oxygen 2 minus. So oxygen was, oh I gotta go back, 5.5, 3.8. 5.5, 3.8 14.0, 11.5. All right, so now we're going to interpolate. You could also estimate, but I'm going to go through it just in case anybody actually wants to learn it. So for 111, our value is 0.203. So we need to know how, percentage-wise, how far away is 0.203 from 0.2 or from 0.3. Just where on the scale does 0.203 sit? So how you do that is I would say 0.203 minus 0.2 over 0.3 minus 0.2 is equal to 0.03. So proportionally, 0.203 is 3% away from 0.2. So now we need to figure out what value of f is 0.3 away from 5.5 and 14.0 for for oxygen and cobalt respectively. All right, so for oxygen, in order to do this, we're going to say, okay, some value x minus 5.5 over 3.8 minus 5.5 is equal to the 0.03 or 3%. From this, we get x is equal to and then we get x is equal to 5.449. Cool. For cobalt, we get x minus 14 over 11.5 minus 14. And that's going to be 13.925. All right, so we have our values for 111. We're going to follow the same thing, except now it's not 3% away. We're going to do the same process for the 200. For the 200, the value is 0.234, or 5, sorry. This is a new distance away from 0.2. It's no longer 3% away. And if we do the math for it, we get 0.235 minus 0.2 over 0.3 minus 0.2. We get 0.35. Or 0.235 is 35% away from 0.2. So what value is 35% away from 5.5? Let's figure it out. 2 minus x minus 5.5 over 3.8 minus 5.5 is equal to now 0.34. This x is equal to 4.92. And for cobalt, the x minus 14 over 11.5 minus 14 is going to equal, and that's going to be 0.34. X is going to be 13.15. Great. So now we have the values that we need for F. Oh, sorry. Yeah, that's not it. These are the values that we need. Oh, excuse me. This is not equal to that. It's equal to 0.03. And then X is equal to this. Okay. We have our values. Great. So we're going to go ahead and write them in up here. 5.45. Oop, that's not there. For 111, we had oxygen is 5.45 and cobalt is 13.9. And 4.92 for 200 and 13.15, so 13.15. Cool. So now that we have these values, I'm going to go ahead and delete all this work. We still need some space. Our F squared, using these equations that we found, or these two equations we found, we're going to calculate F for 111 and 222 in each of our elements, and then we're going to score it. So, how are we going to do that? We have, okay, so for 111, F is equal to 4 cobalt, so 4 times F cobalt, which is this, 13.9, plus, minus 4 times 5.45, which is the scattering factor for oxygen. That's going to be minus 4 times 5.45, 33.8. Right? F200 is going to be 4 times plus 5. I'm sorry, we have different values. It's not 13.9, it's 13.15. Plus 4 times 4.92 equals, let's see, 72.28. It's very small, 33.8. Oh, I'm sorry. That's not right. That's F squared. These are all of our F's. We're going to go ahead and square them. So 72 squared is 5,224. 524. 33.8 squared is 1142. These are what we write. 1142, 5224. Great. So the multiplicity factor is, again, a plug-and-chug thing. So we plug into the... Oh, I'm sorry. The multiplicity factor is not plug-and-chug. The multiplicity factor is... The multiplicity factor is found using a table. So we're going to go all the way down to the table and see that these are the 2 points we use. Because 111 is HHH and 200 belongs to the family of 001. You don't use this one because our shape is an FCC and not an orthorhombic. It is one of the cubic shapes. So this is the only column we're going to look at, row we're going to look at. So our multiplicity is 8 for 111 and 6 for 200. So 8 and 6. Great. The Lorentz factor is where we plug and chug. So we have our thetas from this column, and that's it. All we need to do is figure it out. So LP for 111 is going to be 1 plus cosine squared of 2 times 18.24 divided by sine squared theta cosine theta. And that's going to be 2 times 18.24 and then the that's going to be 36.48. I'm going to take the cosine of that, square it, plus 1. It's going to be 1.647 over the 36.48 the sine of that squared times cosine of 36.48. That's going to be 0.284. Final answer is going to be 5.79. If I made a mistake and calculated it wrong, it's fine. It's essentially just plug and chug and make sure your work is right. I just don't want to check it. Okay, so we do the same thing for the next part, and that's going to be the same process. So, 42.4 looks like cosine of that. Oh, no. Plus 1. 1.545 divided by sine squared times cosine equals 0.199. That's going to be 7.75. All right, so our total intensity is proportional to F squared times the multiplicity factor times the line square, or the last three columns multiplied by each other. So we're going to do that, and that's going to give us 1142 times 8 times 5.79, and that's going to be 52,897. Same thing for the other one, 5224 times 6 times 7.75. 242916. All right, so we found the total intensity. Our relative intensity is just these two values, except divided by the smallest. So here, this is 52,000 is smaller than 242,000. So we're going to go ahead and divide everything by 52,000. So this is going to be 100. Oh. I'm sorry. Divide everything by the bigger number. So 52,897 divided by 242,906. So this is going to be 21% of the height. And this is going to be a 100. Okay, so once we found those relative intensities, we can finally go through the next part, which is drawing the graph. You could have a ruler and do this with a ruler, but it's not necessary. But again, for peace of mind, you could also do it with a ruler. So we know the 111 diffracts first, and then the 222. The angles are going to be 36 degrees about, and 42.4 degrees, because that's going to be double our thetas that we calculated. The 200 is 100% of the intensity. So the 200 has the maximum amount of height. Let's say it's there. If the 200 is the highest, and the 111 is therefore 21% of the 200. So it should be about 20% as high. So this is the 200, and this is the 111. If I did any part of this wrong and you end up getting different answers, it's fine. Just double check your calculations, double check my calculations, make sure it's right. The process is still the same throughout. All right, that's the end of that problem.